Okay, so hello everyone, welcome to my presentation. My name is Golestani. I'm working for RWTH Aachen University in Germany. In this presentation, I'm going to show you how to extract 3D data from 2D video sequences and use them for designing a more efficient motion compensation scheme. So first, let me remove myself, then we can focus on the presentation. Uh, okay. So, this is the outline of the presentation. First, I will talk about the motivation behind this research, then the proposed idea will be introduced. In the third chapter, simulation result on VVC will be analyzed, and finally, I will conclude the presentation. Okay, first, motivation. There are lots of videos around us captured by moving cameras. Daylight road, park running, and marketplace are some examples of such videos in JVET common test condition. There are much more videos used for verification purposes, some MPEG eye test sequences, and even videos captured from video games. The common feature of all these sequences is that they all captured by moving cameras. It's not only these famous sequences. In the new technologies, there are many videos captured by moving agents. Like in autonomous driving or drone, you may want to encode the captured video and send it to somewhere. There are also many videos posted in social media captured by moving a smartphone. Here is a big question. Are the available 2D motion models efficient enough for those videos? This presentation will answer the question and propose a method to reduce the bitrate of VVC up to 5%. Okay, let's have a look at the data to sequence. Here's the estimated 3D data. The yellow boxes refer to the camera trajectory and the gray mesh depicts the 3D scene geometry. The main idea is to extract the 3D data and use them for motion compensation by synthesizing new reference pictures. So there is another big question: how complex is the system? So how complex is the system? If you asked me this question 5 years ago, I would say too complex. However, these days we can handle the computational complexity very easily. So the answer is not anymore. So, for example, these days we have more computational power even in a smartphone. We have access to many 3D reconstruction algorithms performing in real time. Also, new devices are equipped with depth sensors like LiDAR, time of flight, or IMU sensors. This video shows a mobile device equipped with a LiDAR sensor. You can see real-time depth estimation is not a big deal anymore. In this paper, however, we focus on the most general case. I mean, there is no special sensor, there is no information regarding the camera, even we don't know the focal length of the camera, we should estimate everything. Okay, let's see the proposed algorithm. Here is the simplified block diagram of the design system. You can see the detailed block diagram in the paper. The left side is the encoder side and the right side is the decoder side. The dashed lines represents the data needed to be transmitted from the encoder to the decoder. Okay, let's discuss the main steps. In the first step is actually to detect camera motion. As we discussed, we only target the video sequences captured by moving cameras. If there is camera motion, then a flag called flag 3D is sent to the decoder side to announce that okay, the 3D based system is triggered. Of course, if there is no camera motion, the normal VVC encoder and decoder is called. The camera calibration is the second step. In this step, we employ a structure from motion techniques to estimate intrinsic and extrinsic camera parameters. The estimated parameters are then compressed and sent to the decoder side. Just look at the overhead number 1. Here you see some visualization of the estimated camera trajectory surrounded by a point cloud of the scene. For example, here is the camera trajectory, or here is the camera trajectory, the red one. We don't have any ground truths for the estimated camera parameters. However, it can be at least visually confirmed that the estimated trajectory follows the real camera motions. Okay, we have camera parameters. It's time to estimate the 3D mesh of the scene, compress it, and send it to decoder side as the overhead number 2. It's worth mentioning that the decoder doesn't need to do any 3D reconstruction operation. It only receives the encoded 3D data and decodes it. Here, of course, we need to do our best to minimize the overheads. Okay, I don't want to go into the details of point cloud generation and mesh reconstruction. You can simply see them in the paper. However, to reduce the overhead, we should compress the 3D mesh data. To do so, first we decimate the mesh using QEM base method, and then compress it using Google Draco. You can use your own mesh compression algorithm. Let's have a look at the picture here. You can see a sample frame of the park running sequence, and its estimated 3D mesh and camera trajectory. Note that we couldn't estimate the depth data for the quickly moving object like the runners. The original and the compressed meshes from the sample frame's point of view is given in C and D. The original mesh has much more details, however, it's too big to be transmitted to the decoder side. Of course, we remove the details. In this case, we remove the details and keep the basic element of the mesh in order to reduce the overhead. Of course, there is always kind of trade-off between the mesh quality and the size of the overhead. If we keep the mesh quality high like this, we lose the bandwidth. On the other hand, if we simplify the mesh too much or simplify the mesh heavily, we may lower the quality of the 3D of our 3D based motion compensation. In the future slide, we will see how to handle this trade-off. Okay, when we have our 3D data, then we can employ it to virtually synthesize a geometrically compensated reference picture. So how to do that? We can easily warp the content of the regular picture available in the encoder buffer into the camera position of to be encoded frame. This way we generate a new reference picture which is content-wise hopefully very similar to the to be encoded frame. Let's have an example. If you have random access profile and wants to encode a frame number 80, then we should have a frame number 64 as the regular reference picture for motion compensation. The difference between them should be the gap size. A is the to be encoded frame, B is a regular reference picture. As you can see, not only the position of red and yellow boxes are different between the to be encoded frame and the regular reference picture, but also they have different sizes. So C is actually our 3D based synthesized reference picture. We warp the content of B into the position of camera in A while considering the camera parameters and the 3D scene geometry. It's like depth image based rendering. We have the camera parameters, we have the depth data, then we warp the content of B into the position of A and generate C. That's actually the main idea. It can be seen that the content of A and C are very similar. A and C are very similar, especially in the areas we had a good depth estimation. We can't do, of course, anything special for the blue box, I mean the runner's leg, because we had no reliable depth information there. Okay, so then we should put this 3D based synthesizer reference picture into the VVC reference picture list. We have tested two different modes here, the replace reference mode and the additional reference mode. Let's have a look at the plain VTM reference picture list. So, for example, for POC number 10, we have two lists, list 0 and list 1. Each contains of course, two reference pictures. Okay, in the replace reference mode, we use the same list, but we remove the second reference picture and replace it with our 3D based reference picture. In the additional reference mode, we use the same list as the plain VTM, but we add our 3D based reference pictures into the end of the list like this. VVC, of course, takes these two lists and for each CU selects the best reference picture. If our 3D based reference pictures are good enough, then the encoder hopefully prefers them and the bitrate may drop. Of course, after modifying the reference picture list, the plain VVC should be called. Let's see some simulation results and discussion. Okay, look, mesh filtering, decimation and compression have big impact on the final coding. As a reminder, just look at this picture. We first filter out the reconstructed mesh, then decimate it. The decimated mesh goes into the mesh compression block. The block first encodes the connectivity information, how the vertices are connected in lossless mode, then encodes the geometry information, encode the geometry of the vertices, like lossy point cloud compression. We have some parameters needed to be determined, like mesh bounding box size like the decimation factor and geometric quantization parameters. We skip the first parameter for now. You can see the details in the paper, of course. However, the other two parameters are going to be analyzed here. Okay, the decimation factor. Decimation factor is defined as the ratio of the number of remaining vertices after the decimation to the total number of original vertices. A lower decimation factor means a heavier decimation. So the original mesh of the daylight road and the original mesh and the three decimated and compressed meshes are shown here. Here we keep the compression parameters the same, but just study we want to just study the impact of the decimation factor. It can be seen that lowering, like just moving from here to here, lowering the decimation factor causes lower mesh size. I mean a smaller overhead. However, at the same time, it destroys the details. The big question is how to determine the decimation factor. Which one? The decimation factor of 0.5 or 0.1 or 0.0? Which one should be selected? So here is the BD rate for daylight road when we completely forget about the overhead. Of course, the original mesh contains more details and provides the best coding in, and this one provides the worst coding in because it destroys the details. However, when we consider the bandwidth used for sending the mesh to the decoder side, everything changed. Now the original mesh produces a big positive BD rate, meaning that it gets worse than the anchor. And here the best coding end is achieved for decimation factor of 0.1. It provides a good trade-off between the mesh fidelity and the overhead size. So this one is not selected at the best one because of course it has a lower overhead, but it's heavily decimated. Okay, another parameter to be studied is the geometry quantization parameter. Of course, lowering the quantization parameter from 14 to 8 causes very coarse quantization. As you can see, by reducing the quantization parameter to 8-bit, we get a very small but extremely distorted mesh for this one. But the overhead would be very small compared to, for example, this one. Okay, in the table shows the impact of geometry quantization parameter on the coding gain. R1 is the BD rate without considering the overhead, and R2 is the actual BD rate, the real BD rate, I mean with considering the overhead. We have tested three quantization parameters like 14, 12 and 10 for each mesh. We calculated the mesh distortion using d-metric point cloud compression tool. It's clear that there is kind of correlation between the mesh fidelity, mesh decimation and overhead. A QP equal to 14 provides the best mesh fidelity, I mean the best in R1, but a QP equal to 12 actually wins the race. It provides the best compromise between the mesh fidelity and the overhead. So from now on we are going to use 12-bit geometry quantization parameters. Okay, so here we go. This is the complete big table of the result. We have tested 6 sequences in 2 different modes, replace reference mode and the additional reference mode. For each mode we have reported the result for 4 different decimation factor, like this decimation factor 0.3, 0.1 and 0.05 for each. Okay, so as expected, df equal to 0.5 provides the best result if we don't consider the overhead. However, df equal to 0.1 gives the best actual coding gain. The lowest df, like 0.05, generates a very small overhead. So if you compare the overhead, this one with, for example, this one is the smallest overhead. However, the generated mesh are heavily distorted, so it couldn't get the best results in overall. So it means we are going to select df equal to 0.1 to get the best result, at least for our test sequences. It's worth mentioning that the overhead here is the summation of the overhead 1 and 2. So it means like we added up both camera parameter, the overhead due to camera parameter and overhead due to the compressed mesh. Okay, the computational complexity is the main focus of this slide. The simulation result shows that the encoding runtime is quite acceptable. In replace reference mode is even faster than the anchor. It can be justified by noting that our 3D based synthesized reference pictures are very similar to the to be encoded frames. That may help the encoder to decide faster in rate distortion optimization. The decoder, although, is still complex. At the moment, the bottleneck is our virtual reference picture synthesis engine. Recently, we have done some optimization to make it make it faster, and we made it actually around 2 times faster than what you see here. We believe the decoder is still complex, but probably not more complex than some of the new deep learning approaches. So then I will conclude the presentation. We have proposed a method to extract 3D data from 2D video sequences captured by moving cameras and use them to synthesize novel 3D based reference picture synthesis. We could get on average around 3% bitrate reduction over VTM10 with almost the same encoder runtime. Our decoder is still complex, but we have some ideas how to make it faster, and currently we are working on that. I would like to mention that this paper is written based on one of our recent patents. The solution provided in the patent is quite general and can be extended into many video coding scenarios. If you are interested to see the content of the patent, please contact us. Okay, I would be more than happy to answer your question. Thank you for your attention.